Okay, I think the recording has started. Okay, so for the last lecture and today's lecture, like we spent a lot of time in generative models, like where we looked at GDA and several flavors of GDA, right? So there was this one question before we took a break, which is GDA same as LDA? So I think several textbooks introduce GDA as LDA. One reason why I call it as GDA instead of LDA is like not to confuse you with the Fisher's LDA that we have seen, which is not a classifier, but it is just a dimensionality reduction technique. So to avoid confusion, we are calling this Gaussian assumption-based model as a GDA, but don't be surprised if the textbooks call the same model as LDA. Okay, so in fact, there is another third algorithm in the same name, LDA. LDA is probably overloaded in the machine learning community. So there is also latent density allocation, which is also LDA. So there are just too many LDAs. So let's just use GDA for this. Okay, so one thing that like one assumption we took for granted from the beginning is I said P of X given CK is Gaussian, right? So that implicitly means that X is continuous, right? But there are many real life situations where your feature can be discrete. Okay, so let me give you an example problem. Okay, like we are going to consider the problem of text classification. So you will be doing text classification probably in your third assignment, okay, but we are going to learn it much ahead of that. So what is text classification? The idea here is like, I'm going to give you a document, okay? And I want you to classify this document into one out of k topics. Like for example, whether this document is about politics, or it's about sports, or it's about arts, or is this about, I don't know, science, and so on. Movies, right? It's whatever. So given a document, I want you to classify to, let's say, some k classes. Okay, now this is a classification problem, right? But this is not like the toy classification problems that we have seen so far, because in the toy classification problems that we have seen so far, I was always giving you this X, which is a vector, right? It had X1 to XM features. Instead, I'm giving you a document. Document basically a bunch of words, right? Like, so for example, and I don't know, it is rainy, like whatever, right? Like, so I'm writing boring sentence, but like, let's say I have a document with a bunch of things like this. Okay, so now, well, probably this doesn't match with any of the classes that I have, right? Like, so let me just say there's a news about, I don't know, there is US elections coming. Okay, and then it has a lot of details about the election. Now this belongs to politics, right? So how do I represent this document as a vector so that I can pass it to any of the mathematical models that we are developing, right? So there are many ways to do that. So we are going to see one simple way to do this, okay? So the idea here is to consider the entire vocabulary of words that you will see in these documents, okay? Let's say, for example, I have M words totally, okay? Now I can construct a M dimensional feature vector. My feature vector is going to be X1 to XM, okay? Where every entry in the feature vector is one word in the vocabulary. For example, X1 could be A. The second word could be the third word could be, I don't know, Canada, right? And so on. So I have all the words. I'm going to put one here if the word is present in the document. Okay, I'm going to put 0 here if it is not present in the document. Is that clear? Okay. Now, what type of features are they? So these are binary features, right? Like, so these features can be either 1 or 0. These are not real numbers, right? So, okay, so there is a question, do we count the words? If you want to count the words, you can count the words. That is a different representation. But here, my representation for the document is just 1 or 0, whether the word is present or absent, okay? So if I'm just looking at the presence or absence, these are binary features, right? These are binary discrete features, right? Now, in this case, the probability of ck given x is given by probability of x given ck, probability of ck. There's also probability. Okay, so maybe that is, I think that's a mistake in the notes. So let's just call this x comma ck, the joint probability. Okay. Okay, so what is the point of having 0 for words that don't appear? Does x contains all the words? Yes, x is one big vector which has all the words in the vocabulary. Okay, so that is how you can make sure that you have a same dimensional representation for all the documents. Okay, so now p of x comma k is given by p of x given ck, p of ck. Is that right? Okay, so now this p of x given ck, the class conditional density, right? So how do I model this p of x given ck? Now this is not Gaussian, right? So this is a discrete variable. This is not a random, this is not a continuous random variable, right? So now we are going to look at a discrete variant of GDA, okay? So we're going to consider discrete features. So now that I have motivated the model, like we're going to look at the algorithm first and then go back to the text classification again, okay? So we're going to consider binary features, which means xi belongs to 0 or 1. Okay. Now, if there are m inputs, if there are m features, okay. Now this is a discrete distribution, right? So now this distribution is going to have 2 power m numbers in the table. If you have the probability table, you're going to have m binary features. There are 2 power m possible combinations, and what is the probability for each combination, right? Now, how many parameters do you need here? Like you need 2 power m entries in the table. So it's basically 2 power m minus 1 independent variables. Okay, so I think that is also the mistake in the notes. It should not be 2 power m minus 1, it's 2 power m minus 1. Okay, 2 power m minus 1 independent variables. 2, or am I wrong? Is it 2 power m minus 1 or 2 power m minus 1? So you would have, yeah, 2 power m minus 1, this is right. Okay. Okay, so now this is a huge table, right? Like even if you have 10 features, you're going to have 2 power 10 entries. If you have 100 features, which is still a lesser number of features, like you have 2 power 100, which is too much. You cannot learn, this is way too many parameters, right? Like, so now you cannot learn that many parameters with the little data set that we have, right? So this is where the naive Bayes assumption is even more helpful. So we are going to do the naive Bayes assumption again. Okay, so now P of x given ck is going to be approximated with product over I is equal to 1 to m P of xi given ck. Okay, so how do I do that? So I take P of x given ck. Okay, now this can be written as P of x1 to xm given ck. Now this can be written as P of x1 given ck. I'm using the naive Bayes assumption. No, first let's do chain rule. So this becomes P of x1 given ck, P of x2 given ck comma x1, P of x3 given ck x1 x2, and so on, P of xm given ck x1 to xm minus 1, right? So now this becomes, so now this is just chain rule. So this is just chain rule. Now I'm going to make the naive Bayes assumption. So P of x1 given ck is fine. P of x2 given ck x1. Now given ck, x2 is independent of x1. So this just becomes P of x2 given ck and so on. So P of xm given ck. Or in other words, this becomes product over I is equal to 1 to m P of xi given ck. Okay, so now each P of xi given ck can be modeled by using Bernoulli distribution with a single parameter mu ki. Okay, so what is mu ki? So this is basically the probability that xi is equal to 1 given ck. Is that clear? Okay, so now P of x given ck can be given as product over I is equal to 1 to m. Okay, it's just mu ki if xi is equal to 1 and 1 minus mu ki if xi is equal to 0. Okay, so what have I done here? Like, so this is the same trick that we used even for the GDA, right? Like, so like whenever xi is equal to 1, the probability is mu ki. Whenever xi is equal to 0, the probability is 1 minus mu ki. Okay, so now how many parameters that this require for each class? So this requires only m parameters for each class. So look at the reduction. If I don't have the naive Bayes assumption, then I have 2 power m parameters. On the other hand, with naive Bayes assumption, I moved from 2 power m to m. So the naive Bayes assumption makes even more sense. Like, as in, like it's extremely useful in the discrete case, because in the continuous case, the difference is from m squared to m, right? But on the discrete case, the savings that you are getting by having the naive Bayes assumption is from m to m. Okay, so okay, so I think, well, no one asked me this question so far. I expected someone to ask, is naive Bayes a good assumption to have, right? Like, so it seems to be a very strong assumption, right? Like, so is it really true that every feature is going to be independent given the class? Is it going to be true for all the real life examples? The answer is no. So it's indeed a very strong assumption. But okay, so the computation overweights the number of parameters. So okay, Masad, can you be a bit more like elaborate on the question? Okay, yeah. So as I said, it's a too strong assumption, but in practice, it works very well for several reasons. Again, like there are situations where it is the only viable solution, right? Like, because in the case of discrete setting, you don't want to do 2 power m parameters. It's sometimes not even computable if you have more features. So naive Bayes assumption is the only option in discrete case. Okay. The naive Bayes needs more computations. No, the naive Bayes doesn't need more computation. It is actually cheaper than the non-naive Bayes model, simply because it has this strong assumption. Okay, so now let's actually find these parameters mu's. Okay, so we are going to come up with the solution for the discrete case. Okay, so now we are going to consider only the 2-class problem. Okay, okay, maybe a quick note before I continue. So for like some of you, different, like everyone has different motivation to do this course. And for some of you, this might be the first course in machine learning and you want to have a career in machine learning, or like we want to go for grad school in machine learning, or like become a researcher in machine learning. So for people who are thinking about machine learning for life, right? Like, so I want you to take like one way in which you can complement or like have supplement information, like supplement things to the course is, for most of the lectures, like we are going to look at only the 2-class setting. And it's kind of like sometimes trivial, sometimes non-trivial to extend these discussions to multi-class setting. But I would highly encourage you to do these extensions to multi-class by yourself. It might take few hours, but the understanding that you're going to get is invaluable. And the same goes for the GDA discussion that we had, right? Like, so we spent 90% of time on GDA, and then I just mentioned, oh, okay, you change this, it becomes QDA. You change it, it becomes diagonal GDA, and so on. Even though it's a routine, like manual derivation, like if you do it for other things yourself, like you would gain even more understanding. So again, for discrete case, I'm going to do only the 2-class version, but I would highly encourage you to do the multi-class version by yourself if you are serious about learning more. Okay, my voice is breaking. Well, I think it might be the internet connection issue. Um, okay, let me know if it is too bad. Okay, there is a question. I didn't understand the transition from multiplication and Bernoulli. Okay, so let me go back. Okay, so here is the thing. So I want to model m binary random variable, right? So every xi can take either 0 or 1. Now this binary random variable can be modeled with a distribution, because Bernoulli distribution has parameter mu, and well, I cannot restart my system at this point. Let me know if it is too bad. Okay. Yeah, so for Bernoulli random variable, like, so Bernoulli random variables, you have this parameter mu, which is equal to, which tells the probability that the random variable is 1. So, and 1 minus mu is the probability that the random variable is 0. So we are using that fact to model the discrete features. Okay. Is the audio still bad? Okay, so, well, I'm trying to keep the external mic as close as possible to me, but there might be some issues with the internet. Okay, I'm sorry, I'm not sure what to do. Okay, okay, anyway, I cannot restart right now, so I will fix it before the next lecture.
Maybe stopping your camera
we're going to consider the 2-class problem. Okay, so okay, but maybe that makes the lecture like, I'm not sure if there is anything. Okay, I get a notification that the internet connection is unstable, so maybe it's the internet issue. Okay, so let's start with the 2-class problem. Now, the likelihood is given by, again, we are going to do the same maximum likelihood solution. So the likelihood is given by probability of D given what are the parameters that we have for 2-class problem. Okay, so what? Okay, so I'm not sure what to do for the audio. Maybe let us. Yeah, so we only have 20 minutes left. So yeah, so let's continue. But I will fix my audio quality before the next lecture. Okay, so parameters that we have. So we have the mean, right? Like so mu1 and mu2 for the Bernoulli, and we also have the prior. So mu1, mu2, and the prior probability. Okay, so for Bernoulli, for Bernoulli distribution, like you only need mu1. So like it's not like Gaussian. Okay, so now the likelihood is given by product over n is equal to 1 to capital N. Okay, so with probability phi, it could be from class 1. In that case, the PDF is given by summation over I is equal. Okay, it's not PDF, like it's a discrete probability. Okay, so pi is product over I is equal to 1 to m, mu1i xin 1 minus mu1i 1 minus xi. Okay, it looks like a very complex term, but what it really means is also it's like we have pi and the product. So this is actually the prior probability pi, okay? And then you have the product term, which is the probability for the x, right? Similarly, you could also have, okay, so now this is for class 1. Now if it is class 2, you're going to have 1 minus pi times product over I is equal to 1 to m mu2i xin 1 minus mu2i 1 minus xin, the whole thing power 1 minus t of n. Okay, so now this is actually a very complex equation to deal with. So let's just call this whole term as x and call this whole term as y. Okay, so now this becomes ln probability of d given mu1 mu2 pi is equal to summation over, okay, I'm switching from likelihood to log likelihood. So it becomes, some product becomes summation over I is equal to 1 to n, sorry, n is equal to 1 to n. You have t power n ln x plus 1 minus t power n ln y. Okay, now we want to differentiate this with respect to mu1i or mu2i, right? So now dou ln probability of the data given the parameters divided by dou mu1i is given by dou by dou mu1i. So remember that there is no mu1 in the second term, right? So it is just the first term. So we are already cutting 1/2. So it is just the first term. So it becomes summation over n is equal to 1 to n, okay? T of n ln mu1i power xin 1 minus mu1i power 1 minus xin, okay? The whole summation. Is that clear? Okay, so now this is again another simple differentiation. Like it, so the thing is, like, these equations look big, but the properties that they are using for differentiations are still very simple. Okay, so now let's start with this. Okay, so now I want to differentiate this. So this becomes dou by dou mu1i of summation over n is equal to 1 to capital N. So T of n, okay. I'm just going to things together. So like xi n times ln mu1i plus T of n 1 minus xi power n ln 1 minus mu1i. Okay, so now we need to differentiate this and set it to 0. Differentiate and set it to 0. So summation over n is equal to 1 to n, t of n, xi of n, ln mu becomes 1 minus mu, okay, plus t of n, 1 minus xi of n, ln 1 minus mu becomes 1 by 1 minus mu 1 I. And you differentiate 1 minus mu 1 I again, it gives you minus 1, and the whole thing is equal to 0. Okay, so now this becomes summation over n is equal to 1 to n, tn xin multiplied by 1 minus mu 1 I plus tn 1 minus xin multiplied by mu 1 I. And there is a minus symbol, so let's just make this as plus, sorry, minus. Okay, and the whole thing is equal to 0. I don't care about the denominator. Okay, so now you just expand these things, then you get the answer. So summation over n is equal to 1 to n, tn xin 1 minus, okay, so minus tn xin mu 1 I minus tn mu 1 I plus tn xin mu 1 I, and the whole thing is equal to 0, right? So you can see that these two terms cancel. So this becomes summation over n is equal to 1 to n, tn mu 1 I is equal to summation over n is equal to 1 to n, tn xin. Okay, so now this become, okay, so now we are just carrying about mu 1 I, right? So mu 1 I is given by summation over n is equal to 1 to n tn xin divided by summation over n is equal to 1 to n tn. Okay, now let's, if you did not follow the derivation, it's fine, you could go back and redo it. But let's just try to understand what this mu1 means. So remember, mu1 I is the probability that a feature is 1, given it is from class 1, right? So what are we doing here? We are essentially counting the number of times tn is equal to 1 and xi is equal to 1. And you are dividing it by the number of times t is equal to 1, right? So another way to look at this is mu1i is equal to number of examples where xi is equal to 1 and t is equal to 1 divided by number of examples where t is equal to 1. Okay, so similarly you could also write for mu2i. I'm not deriving it, so you could derive it, and it is number of examples where xi is equal to 1 and t is equal to 0 divided by number of examples where t is equal to 0. Okay, now you could compute pi by yourself. Pi is going to be the frequency of classes. It's the same as the continuous case. Okay, so what have we done here? So we considered binary features, and the maximum likelihood solution in this case is simply counting things, right? So now similarly, if you want to generalize this to discrete features which has more than 2 possibilities, okay, so in that case you're going to have some categorical features. Okay, so when the moment you move to categorical feature, then you could do the same derivation, and you will see that the parameters are going to be the frequency of occurrence of each of these category in the given class. Okay, okay. So now let's go back to the text classification example. So remember that P of ck given x is equal to P of x given ck, P of ck, and there is a normalization term like which I'm not considering for now. So this is equal to product over I is equal to 1 to m, P of xi given ck, P of ck, right? Okay, so I could do this naive Bayes solution, like I'm going to get the probability for ck given x. Okay. Now there is a problem in doing this approach. Can someone tell me what could go wrong if I compute p of xi given ck for every word in every topic? So we are doing document classification. And what does p of xi given ck means? It just means that, okay, so, well, yeah, so let's just say it's proportional. It's not equal to. Yeah, so, yeah, you are right. It should be p of x, ck, comma x. So let's just make it proportional. Okay, so now what could go wrong when I try to estimate p of xi given ck? Basically, the probability of a word given a class. Any answer? Okay. There are a lot of possible words. Some can belong to multiple class. That is okay. That's not a problem. Any other answers? Okay. Some misclassifications does not have a probability. Why? That is a problem, but why is that happening? So it might happen because there might be certain, okay, here's the thing. The vocabulary has too many words, right? So probably you would have like 10,000 words in the vocabulary. And now given a data set, for example, consider the class politics. So maybe you don't have the word apple at all in the politics, right? Or maybe you don't have the word, I don't know, football at all in the politics. Maybe you could have football in politics, but the point is there are many words which are not going to be there in every class, right? So for those words, the probability of xi given ck, since we are just counting the occurrences, is going to be 0. So when one word has a probability of 0, then the whole term, since it is a product, is going to become 0, right? So most often you're going to get 0 as the answer, but in reality, like there is some probability for every class, right? So this is not a very useful classifier. Now, how to avoid this? So the issue, I'm going to rewrite the issue. The issue is, given limited examples per class, we might not see all words appearing at least once in all documents for every class. Okay. So, or in other words, if xi is equal to 0, whenever t is equal to 1, let's say that xi doesn't occur at all in t is equal to 1 case, then mu1i is going to be 0, which means the probability of ck given x is also going to be 0 often, right? So we don't want this to happen. So there is a way to avoid this issue, which is the idea of Laplace smoothing. Okay, so in Laplace smoothing, so we are going to assume, like basically instead of counting to 0, we are going to start the count from 1. Okay, so mu1i is given by number of examples where xi is equal to 1, t is equal to 1, divided, this is the original formula, right? So number of examples where t is equal to 1. Now this is the original formula. So I'm just going to add a +1 to the formula and add a +2 here because there are two possibilities, right? So if I just start fresh and I don't see the word at all in a particular class, then the probability is going to be 1/2, right? So it's a 50-50 chance for the classifier, which makes sense, right? Like so basically, if no example from a class, then it reduces to a prior probability of 1 by 2. Okay. Now, this idea of Laplace smoothing is actually adding a bias to the model, right? Now, this adds a bias that if you haven't seen any examples from the class, then the prior probability for any word is 1 by 2. Okay. Now, as you see more and more examples, okay, so this equation, as you see more and more examples, as this number becomes higher, the probability is going to shift. Okay. So for example, let's say I have seen 100 documents and I haven't seen, let's say I have seen 100 politics documents and I haven't seen the word football at all. Okay. Initially, when I haven't seen any politics documents, the probability is 1 by 2, right? But when I see 100 documents and I haven't seen football at all, then this probability reduces to 1 by 100 plus 2. So it's 1 by 102. So the probability will go close to zero as I see more and more documents. So this is a bias which will decrease as I see more examples. Is that clear? Okay, so maybe I also wanted to cover different evaluation metrics for classification, but we will do it in the next lecture. But your assignment 2, which will be released today, might have different evaluation metrics. Don't worry, like start with assignment and we will see the metrics in the next lecture. I could take a couple of questions. Any questions? Alaji?
Yes, so in the naive basis assumption, we use the Bentley model, and I didn't understand why we had to do the excuse me, why we had to do the I'm looking for it. Sorry,
Sorry, why we have to do?
I just looked for it. I just forgot how to name it. Yeah, the chain rule. I didn't understand why we had to do this.
Uh, which part are you talking about?
So in the naive Bayes assumption, right after the
Yeah.
discrete figures, yes.
Hmm?
So I did
Yeah.
not understand the point of the chain rule.
Oh, okay. So no, this is okay. So this equation is just, I was just deriving this equation here. So basically, like you start with P of X given Ck, which is P of X1 to Xm given Ck, right?
Yes.
Now, one way to write this is by using the chain rule. And then I say that, okay, hey, so if I follow naive Bayes assumption, then this term could be replaced with this term.
Oh, okay, okay, okay,
No, this is just like an expansion of the naive Bayes assumption.
okay, okay, okay.
Okay. So there is a chat which asks, will the office hours still happen during the break week? Well, I don't know. Is it normal to have office hours during break week? So this is supposed to be a study week, right? It's not a break. Is it a break or study week? Okay, it's a study week. So probably we could do the office hours.
Yeah, well, I can get invested more. Yeah, I'm not sure about 30, but yeah, there are office hours during the study week.
Okay, yeah, so we will do the office hours. So I will also do my office hours, which is 2:45 to 3:45, but just the office hours, like there's no lecture. Okay, any other questions? Or I could stop the recording. Okay, so I will stop